Now over here you can see a sample linear regression. You're applying here the same concept. Okay, you're applying here the same concept, just you are just differentiating the y-intercept term and the slope terminology. You are just differentiating the notations for the y-intercept and for the slope of the coefficient of your, which is behaving as a coefficient of your independent variable over here. Because I remember that when we were discussing the fertilizers influence on the production of the bushels of corns. So over there we were taking fertilizer as the independent variable, because once the fertilizer is good, that it is going to put impact on the production. It is going to boost up the production. And if the fertilizer is of bad quality, or if it is of just a third grade quality, then it is going to decrease the bushel production or the food production. So production of the food is depending on your fertilizer. Over there the fertilizer was behaving as your independent variable, and your bushel of corns was behaving as a dependent variable y. Remember? So over here we have just obtained the same format that we did in the beginning when we were discussing our population statistics. Okay, so right over here, this thing. All right, so same story we're going to repeat here. The same equation, the same format, just the notations are different. We are taking we are just picking the sample data out of this huge population data, and then like instead of making a survey of the entire population, we just pick up out of millions of the population countrymen. We just selected 1,000 and we just compile the data of the 1,000, and then we just make our we just put down the inference, and we just get the result. And on the basis of that result, we just obtain what could be the best possible answer of our beta naught and our beta 1. So here you can see that this one, this is the equation of your sample data. So you can see here that yi is your actual value, which is behaving as a dependent variable on this independent variable x. Okay, b1 is the slope of the line of the best fit that we are going to obtain once when we plot all the values of your actual sample data on the 2D graph. We get a scattered plot, and then with the on the basis of that scattered plot, we just put our analysis and we try to maintain a best fit line. Once the best fit line is so obtained, we just view where the line of the best fit is intersecting your y-axis, and that's said to be our y-intercept, and we just call it b naught. Okay, with the help of the b naught, we will be able to predict what could be the best possible answer of our beta naught, that is the y-intercept of our population best fit line. And this is the slope of that sample best fit line, b1, and b1 is going to help us in estimating the best possible answer of our beta 1, that was the slope of the best fit population line. And here e is actually the random error. Okay, and you can see that the random error we obtain by subtracting the actual value with the predicted or estimated value, right? So that was the error. So as I told you in the beginning, why we are adding the error value over here. This is the estimated value of y. Okay, we add up the error in it, we are going to get the actual value of y. So this is the equation of obtaining the actual value of y with the help of the predicted line, the line of the best fit. Okay, so you can see here they have represented the estimated value of your y by your y cap instead of using y dash that I use in the early slides. So this is your y cap, and this is representing your estimated answer. So actually this is your y cap, this whole thing is your y cap. you know that y minus y cap gives you the error. So if you just shift the y cap over here, the negative sign becomes positive and you just get y cap plus e. So this is going to give you your actual answer. Okay, like over here I just tried to plot a scattered diagram, okay, on this 2D graph. Okay, this is actually your x-axis, this is your y-axis. So this is the scattered plot, and I want to assign the best fit line that can that should cover a maximum point on it, and the remaining one should be as close to it as possible. That is taken as a line of the best fit. So let me assign a line of the best fit over here, and for example, the best fit line in my views is this. Okay, you can see the maximum points are close to it and a few points are lying on it. Okay, so the line of the best fit actually varies if we just try to analyze it on our own way. Okay, so how about this one? This also can be the line of the best fit. How about this? Okay, so there are several ways of obtaining the best fit line, so that's why we are very much concerned in obtaining the accurate line of the best fit. So for that purpose we just take the help of our calculus, and we just assign the best possible y-intercept and the best possible slope of the particular line of the best fit, and then we form the equation on the format of y is equals to mx plus c. So that is the complete derivation that I have just sent you on this through my snapshot, and that is my personal work over there. We are not discussing that thing, but actually I just want to put down the acquaintance for you that the best fit line is not something that is analyzed but just by viewing. We need such y-intercept and slope value of the line that should give us the best possible answers, and that should give us the minimum error value. Okay, so this is it. Now as you can see, this is the line of the best fit, and these are the actual values that we have obtained through the data sample. Okay, and corresponding to the particular x values. Okay, so if I just talk about my estimated values, so if I just discuss this value, this is the actual value corresponding to this value of your x. Okay, this is lying over here. And if I just say that this is my actual value, and with respect to this x value, if I just put down the projection, I will see that where it is actually falling. So I will come to know that it is on the best fit line, it is falling over here. Okay, it's falling over here. So in this respect, the particular the subjective or the corresponding estimated value of your y is over here. Okay, and the actual value of your y was lying over here. It was lying over here. Okay, so this is your, for example, just assume that, let it be, for example, it is, the value is your 15 here, and for example this value is your, for example, it is 12. So the distance or the difference between these two answers is your 3. Okay, so you can say that the distance between my predicted value and the actual value is the error, and we call it E. Okay, we call it E. So if this value is, for example, x1, then the corresponding y1 value, the predicted y1 value is this. This is your y1 cap. Okay, and this is your actual y value. All right, so it is just y1. It is y1 cap. This is x1, and the corresponding error is your e1. Okay, so I'm going to write down, you know, that your y, the actual value, minus your estimated value is equals to your error. Okay, so the error 1 is so obtained by subtracting your y cap 1 with your y1. Okay, and you know that your y1 cap is equal to this equation. Okay, this is the b naught and this is your b1. You see that this is your b naught because this red line, the line of best fit, is cutting your y-axis at this point. You can see this is cutting your y-axis at this point, all right? So this is your b naught, all right? And the slope, you know well how to calculate the slope, the rise over run, and the formula I have just mentioned in one of my previous videos. So you can calculate the slope by taking any 2 point lying on the line, and you just get it with respect to your this answer. It is your this y2 minus y1. Any two values you select. Okay. Upon the corresponding x2 minus corresponding x1. That's how you obtain the value of your slope, the slope of the line. And you're going to substitute over here. And you're going to form the best equation. There it is. That's it. Okay. That's it. So this is your y cap. So over here, as I've just said, that this is your y cap. So it is going to be y1 equals to your y1 cap. We are discussing here the sample. That's why instead of using epsilon, we have just differentiated our error with our e. So that's it. Okay, now over here you just put down your answer, your equation is b naught plus b1 x1 plus e1. So this is going to give you the first value, actual value of your sample data, right? So that's how the equation comes. And as far as what else is left, I told you that once you calculate your b naught and your b1, with the help of that you are good enough to estimate your beta naught and your beta 1, because it is too time consuming to make the survey and then compile the data and then the scattered plot and then forming the best regression fit and then get the value of your b naught and b1. So it is a heavy task. So we just select the sample and then we obtain the equation. We got the b naught, we got the b1, and this b naught and b1 is going to help us calculate the value of our beta naught and beta 1. And how we are going to calculate that? For that purpose, we are having a proper systematic process. That is a t-table process, a t-distribution. We are going to refer in order to get the value for beta naught and beta 1 with the help of b naught and b1. And that method was also introduced by the Carl Pearson, and it is a long method and it needs a separate lecture for a complete briefing. Okay, so that's it up till now, and see the next thing